Howdy folks, Mr. Reed here, and welcome to one more question. So what we're going to be taking a look at today is algebraically determining what the inverse, I'm going to say to a function is. I'm going to look at a couple examples, both of which are going to be a function to begin with. They wouldn't have to be in order for this to work out, but I'll make some comments on things that we're going to be careful with notation-wise when we do these questions. So we can do this without a graph. If you want to see it done graphically, take a look at my last video, but this is for algebraic work, so if that's what you're looking for, let's get to it. Okay, so I have a couple examples up above. First one's linear, second one is quadratic. I'm going to take a look at how to determine the inverse, maybe function, maybe relation to these particular original functions. So we should be comfortable, depending on where you're coming from, that might not be true, but this is a linear function. All linear functions are functions except for if it was a vertical line, then it wouldn't be, but this one's not. It has a slope, a defined slope. And then the second one is a parabola. Those are all going to be safe too. So we're pretty much definitely functions. They're both written as f of x. I guess it should probably use a g of x for the second one or something, but I'll just do them separately so it's not really an issue anyway. So first things first, I'm going to just copy down a. So that says that f of x is equal to 7x minus 11 over 3. Now, what I want to do is I want to take the first step. I want to be careful because when I switch my x and my y values and this thing becomes the inverse, because this is the original that I've just written down, there's a possibility that it will no longer be a function. So I'm going to switch the way this is written to just saying the y values are equal to 7x minus 11 thirds. It might not seem like a big thing, but until I know for sure that this thing is going to be okay to call an inverse, I'm going to refrain from having either the function or inverse function notation being a part of the algebra. So first step, I'm going to rewrite this as being x is equal to, I did a couple equal signs last time. Anyway, I should probably fix that. And 7y minus 11 thirds. Okay, so the idea here is that typically we'd like to represent this new function or relation in terms of y is equal to as well. This is technically going to give me the correct relationship, but let's just see what happens if we solve this thing for y. So the reason why we switch the x and the y values, if you didn't see the last video, is basically what we want an inverse function to do is where we used to have x's, those are our input values. They created a set of output values. The inverse is supposed to take those output values, the old y values, and turn them into our new inputs. And when you put those inputs in, it should give you the outputs being the old inputs. So your old y values should be giving back your old x values. So we can kind of force that to happen by just switching the x and the y. We saw that graphically. We switched the x and the y coordinates of each point, and that worked out. If we do this algebraically, I'll tell you the reason why it at least seems to work from a logical point of view. What we're going to do is we're going to rearrange this for y. How do we do that? Well, we're going to use kind of like inverse order of operations to try to isolate the y. So right now it's multiplied by 7, and we subtract 11 thirds from it. What is the inverse operation to subtracting 11 thirds? Well, we'd add 11 thirds. So we add 11 thirds to both sides of our equation to make sure that it still equals, and we get something that looks like this. Next up, we're going to divide both sides of our equation by 7, and so then we would have the y all by its lonesome. But why would this give you back the original values? Well, last time, if you look up at the beginning, we were taking a number, multiplying it by 7, and subtracting 11 thirds. So how would we get the original number back? We'd add 11 thirds and then divide by 7. So the exact inverse set of operations in the opposite order that we first did them. So we are adding 11 thirds and we are dividing by 7, and that will give us what we're looking for. This is algebraically going to be true. However, we can make this a little bit nicer because not only is this thing going to be a relation it is actually also a function. So we can write it with inverse function notation. So f to the -1 in the exponent type position there, so the superscript of x is equal to, and then I'm going to just tidy this up a little bit just because it's a little sloppy to have the fraction up in the numerator of a fraction. That would be the same as 3x plus 11 over 3. So I put the x on a denominator 3, so I would multiply the original denominator, which is 1, by 3, so the numerator x gets multiplied by 3 as well. But also this thing is all divided by 7, which I'm going to take one more line to kind of draw that out and show you. So if you have a division and then another division, we can actually just smuck those together by multiplying. If you're not sure that that's actually the case, think of the 7 as 7 over 1. And you probably remember a rule somebody said to you somewhere along the way that says if you have a fraction or anything and you divide by a fraction, it's the same thing as multiplying by that fraction's reciprocal. So we're going to multiply this by 1 over 7, which will put the 7 down in the same denominator position as the 3, which will give us 3x plus 11 over 21. So that is the linear function that would go along with the inverse. Again, if you really wanted it to be kind of in that y equals mx plus b form, just take the 21 and put it on both terms there. So it would end up being 1 over 7, so x over 7 plus 11 over 21. And again, it doesn't really matter what the form is. We've isolated this for the y value, been able to state that it is actually a function because that is a linear function that we have there, and go from there. So I am going to switch this over to part B. So in part B, we have f of x is equal to -2 x plus 3 squared plus 5. Okay, so in this layout, we have a parabola. It's a downward facing parabola, blah, blah, blah. It has a vertex at -3 comma plus 5. All that stuff doesn't really matter, although you might be able to tell in your head. If you've seen the graphing inverses video from my last one, if you were to, in your head, perform a horizontal line test on a parabola, you're going to see that it fails in many locations. Actually, anywhere where the graph exists other than the vertex, we're going to have some problems there. So we're going to assume probably that this is not going to be a nice function as its inverse. That's okay. We're going to rewrite this as y is equal to, again, -2 x plus 2, oh sorry, x plus 3 it is, x plus 3 squared plus 5. All right, so same thing as last time. I'm going to basically just take this and flip my x and my y values. If I do, I get something that looks like this instead. Now, just for the sake of most of the way we do these algebraic representations, we're going to rearrange this thing for y. And again, it's kind of good to see how the inverse operations work when doing things the other way. So this y right now, you'd have 3 added to, oh sorry, let's go back up to the original. The original x, you'd have 3 added to it. And then you would square that whole thing. Then you would multiply by -2, and then you would add 5 to it. So if we were to go backwards, we would have to subtract that 5, and then we'd have to divide by the -2. We'd have to undo the square, probably a square root, but we'll talk about that in a second. And then we'd have to subtract 3. And that's basically going to be what we end up doing here. So first step, we'll subtract that 5 from both sides, and then I'm going to go ahead and do the next step as well, which is going to be dividing it by -2. If I do that, I'm going to be left with this bracket squared on the right-hand side of my equation. And so, like I said before, I have to figure out what the inverse operation to a square is. Now, this is the part where it's a little bit trickier, because if I do the square root, which logically should be okay with the fact that that is going to, in fact, be on the right trail for the inverse to a square. Square root, sounds okay. However, when I do that, I'm going to, because of the way that the square root symbol, what it represents, I am going to get the principal root of the stuff that's underneath of it, which means it only kicks out the positive value. So if you have a square root of 9, for instance, that's 3. But if you were to have x squared is equal to 9, something squared equal to 9, you're allowed to have 3 times 3 equal to 9, but you can also have -3 times -3 being equal to 9. So the principal root tells me I just care about the positive. But originally, I had something squared is equal to the part that's on the left. And so that something squared could have been a positive value, but it could have been a negative value too. So this part right here could be positive or negative, and I need to make sure I'm still keeping track of that. So when I take the square root here, I need to acknowledge that there could have been 2 answers to this. It could have been that that root is positive or that root is negative. So now I'll just continue. I'm going to subtract 3 from both sides and get -3 plus or minus the square root of x minus 5 over -2. And that plus or minus the square root probably reminds you a bit of the quadratic formula. And there's good reason for that, because in that case too, if you're coming up with a quadratic formula, you probably did that by completing the square. And when you do that, you need to acknowledge that there could have been a positive answer and a negative answer. So when you undo that square as part of completing the later stages of that, after you've completed the square, then you need to make sure that you are taking into account both values. So we've done that, and now we have an expression for y that has 2 options. So -3 plus or minus the square root of x minus 5 over -2. This automatically, for most values, is not going to be something that could be a function, because we are getting 2 y values probably for a lot of different cases. Again, if you kind of had this picture in your head of what a parabola looks like originally versus what the inverse is going to look like, depending on, I don't remember. Mirrored images in my head aren't real good, so I don't know how I'm showing up on the screen. So it's going to be one of those sides, a parabola that's facing off to the side, which is going to be our inverse relation. But that thing is going to have 2 y values for most of the graph, other than the vertex area or the place where it's not defined in the first place. So this one, I am not going to switch up that y and put it as an x to the -1 in the superscript position, because that would imply that I have recognized that this is a function. I've actually done the opposite. We've recognized that this is not a function, so this is just a relation. That's what the relation is. We'll leave it the way that it is right now. I wouldn't necessarily feel like this is a requirement, but some people might not like the negative sign that's in the denominator. So you could just multiply top and bottom by -1 and make it look like that. Maybe it's a little bit cleaner, but it's not really a big deal either way. So if you found that one helpful, like, subscribe, and as always, take care, folks.